Okay, so I'm going to make a start. So again, thank you for joining me today for our second English webinar, CAE Technologies for tube roll design and subsequent processing. My name is Carl Stevenson and I head up Data M's UK operation for sales, support and service. I also look after the North American market as part of my role. I've been a Copra RF user now since 1994, and since joining Data M I've been a Copra FEA RF user since 2009. Primarily I'm an open section design specialist, and previously I've worked at two of the largest UK roll forming companies. More information on myself and my colleagues can be found at the Data M website. So today's topics, we're going to be talking about product development with Copra CAE Technologies. We're going to look at an example of tube roll design with various gauges, adapting these technologies, and then finally looking at some subsequent processing, some possibilities beyond the roll forming process itself using these technologies. So firstly, what is CAE? CAE is computer aided engineering, and as you can see here, the Wikipedia definition of that, it's the broad usage of computer software to aid in the engineering of analysis tasks. For example, CAD, computer aided design, computer aided manufacture, are all elements of computer aided engineering. Now, these are just a few, of course. So now let us consider how Copra, or Copra's computer aided engineering technology. Essentially part of the Copra suite of products, as you may all well be familiar, we have Copra RF, which is design, the CAD side of things for developing flare patterns, profiles, roll tool designs, and theoretical strain analysis. In addition to this, we have Copra FEA RF for simulation, finite element modeling tool. And in addition, we have our Copra profile scan and our Copra roll scanner, which is computer aided quality management. Essentially, we can use this tool to capture information also from our roll tools itself, to give us comparisons to the designed profile, roll contour. For accuracy, we can also use this for reverse engineering, for feeding back our roll tool geometry of legacy projects whereby we may not have any CAD data any longer, to the Copra system, again then for subsequent verification, simulation with Copra FEA RF. So that's a little bit about the Copra computer aided engineering technology. So the question is, why use computer aided engineering technologies? Well, if we consider the time frame to develop new roll tool sets back in 1985, which is some 30 years ago now, the overall product development time here would have potentially been taken up with approximately 20% of the design time being done on 2D drawing boards using a pencil. And the subsequent raw manufacture itself would have been done using templates generated from these 2D drawings, and following this there would have been a machine setup, the verification of that tooling, and we could be looking in the region of 80% of the overall product development time to verify that profile, that product. If we roll the clock forward a little bit, some 15 years to 2000, we now can see some significant changes already. So it's quite commonplace to use software like Copa RF for design. So we had a slight increase in design time here, but now we're looking at theoretical strain values. So hopefully we're getting a better understanding of the work our material is doing. And in doing so, the end result is ultimately a reduction in the machine setting time, the machine setup, the verification of the tooling, because already we're using the computer technology, the software, to help us reduce strain in the design. And overall, if we consider that against the original product development time for a new set of roll tools, there's an approximate time saving of circa 15%. Now if we consider modern day, so the situation now in 2015, we also now, or it's quite common now, to use tools like Copa FEA RF for analysis and verification of that roll tooling. And of course it's quite obvious to see here there's an increase in design time now, which is always the battle for acceptance with the board and the production teams within an organisation. Clearly, because we're now telling them we're going to extend our design time and not reduce it. However, in doing so, what we're able to do is aim to develop right first time roll tool sets with the aid of computer aided engineering technologies and ultimately reduce waste, material and time. At the machine setup, you can see here there's been a significant reduction now. We're looking in the region of 15% of the overall original product development time, and thus an overall time saving now, we're in the region of 40% time saving. So this is a significant difference compared to 30 years ago. So we can try and put some numbers on that, just figuratively speaking. With a traditional design process for a large project, all process improvement is carried out directly on the machine, and the only problem and downside of this is that's increasing our costs all of the time. So if we can imagine if we had to replace a good percentage of the roll tool set on a large project, we could be looking in the region of €7,500. Wasted sheet material, for an example, we could have ordered the incorrect strip width because we were unaware of the effects of the neutral line changes. The labour cost of the operator to test, set up and configure these rolls, manufacture rolls, and of course the cost of opportunity. I mean, we have a conservative figure here of around €40,000, but it could be much more. So if we imagine for a large project, we could be looking in the region of €55,000, €56,000 here. So now if we take that same example, and whereby we're now using software technology, the process upgrade is taking place during the design phase, as I said in the previous slide. So of course there's some software amortization to consider now, because we need to pay for the software, of course. Hardware amortization, I guess this could be negligible. And the cost of the labour cost of the technician is in the region of €4,000. So you can see here between the two, we're saving almost €51,000. This is if we consider how many rolls we would have changed during a optimization process of a large project using today's methods or the methods of 30 years ago. So with a conventional rolled product development process, we're aware we would develop a forming strategy, a design, generally done in two-dimensional form with a pencil, and constructing some angles and a flare pattern manually. Afterwards, we would create a roll tool design, maybe even on the 2D drawing board. This is before CAD. Roll tool manufacturers I mentioned previously would probably be done with a template. And verification would probably be done with maybe soft rolls as opposed to heat treated rolls, so we can easily modify them. Hopefully save some time and cost there. If the quality is acceptable, of course, we deliver the project. And if we need a lot of know-how and experience to work through this, this loop. If the quality is not acceptable, there are additional costs, time and effort to deliver that project. So we'd have to readdress the forming strategy, the tool design and the roll tool manufacture itself, again resulting in verification. And we would continue this loop, potentially modifying rolls, manufacturing new rolls, developing the forming strategy until we received a quality product. So now when we consider things using COPA technology, we develop a forming strategy in the electronic world in CAD, using the software to unfold our geometry and calculate our neutral lines, look at strain for forming angles and so on. The roll tool design is also constructed with the software. Certainly with tube profiles, it's pretty much automatic. It's a lot less labour intensive because we're working on a round shape and it's parametric. The verification of our roll tool design and our forming strategy is then done using COPA FEARF. And we're able to then assess our forming strategy and roll tool design in the virtual world without any rolls being manufactured. And the optimization loop continues now without adding any additional cost. So the time and the effort is the only thing required, as I said, an increase in design time to achieve our end goal. If we're happy with this quality, we then move on to the roll tool manufacturer. With the traditional approach, quite often we have to use the strategy that we think beforehand is the best one. Maybe it's a strategy we're used to using or we've used in the past. And due to the associated costs, new or alternative ideas may not be considered at the design phase, and the preferred, easier approach or the known examples are used, which may not be the best solution, of course. When we design with FEA, we can actually test several strategies without obtaining any prohibitive cost of that, other than the time to simulate and post-process. So therefore, for this reason alone, quite often you would generally only be reconsider additional strategies when there are problems at the machine. In other words, when the costs are already at their highest and the most difficult time to implement a new strategy. So if we now consider the possibilities here, I apologise, this is an open profile example. But here you can see we used, and the strategy at the top here, a familiar approach to forming a Z profile, because this is the known approach, the norm within an organisation. And you can see we were achieving here twists of around 35 degrees per metre. So we ask ourselves, what would the solution be at the machine? And what would it cost to solve this? And more importantly, who will pay for these changes? Because once we've quoted the cost of a set of tooling to a client, we can't generally go back and ask for additional funds to implement a strategy change due to a problem we found during verification. And more importantly, whose idea would we try first? And how long would it take to implement any changes? Because quite often when we have a situation like this, the easiest approach or the cheapest approach to fix the problem is the one that will be taken. Whereas, again, it may not be the best. with finite element analysis, as you can see here in strategy 2, with FEA you can entertain strategies that would otherwise be ignored at no additional cost. If we were to take this approach here in strategy 2, and we were unfamiliar with that, it's quite a gamble. There are unknown, reasons not to go this way, and certainly if it didn't work, the guy suggesting it, he may lose some credibility because of the cost of the role tool set we've just manufactured. In the virtual world, there is essentially no cost in this way. If we again consider the traditional approach, the access and visibility is very limited within the roll former. It's essentially a black box. We can't see what's causing these problems, which of course is unfortunate. When designing with FEA, we have full access and visibility to what's happening during the process. We can gather an understanding of what's actually happening within the material, and we can determine the forces acting upon the strip, elongations that could be caused by these forces, and we can obtain a true three-dimensional view of material movements that are actually taking place during the forming process. And we can even quantify problem solutions normally only encountered at the machine. We can establish what is actually causing it and not just surmising what's happening. As you can see here on the right, for example, the upward material movement as we enter the station, and the problems is caused being oil canning and the high forces on the return legs cause an elongation, and thus we have some flare here on this profile here of some 3.7 millimeters. So another reason to consider using computer-aided engineering technologies such as COPRA is to enhance our company know-how, and this is to build our company's experience and enhance the company-specific know-how, and this is the base for a continuous improvement process within an organisation, as this leads us to be considerably more competitive. You can see here on the FEA timeline we have the starting point of FEA, whereby we would need to build on this experience, and we can then verify the known problems we may have in existing roll tool sets or at the machine and new designs. And in doing so, what we're actually doing is becoming an expert, and the system, the processes, becomes fully integrated into the process chain. As we continue our journey, we can then look at driven rolls, considering high strength materials. We can think about extremely thin wall profiles when we think about those high strength steel materials, profiles. And the tight tolerances, which are quite often now associated with rolled products. More often than not, we're now seeing shapes which would previously have been extruded, roll formed, and being held to such tight tolerances previously only experienced in extrusion. Additionally, product quality is another reason to consider using these technologies. We can see here the more software we have available. So product quality in the old days over here on the left hand side of the graph. Oh, sorry. And then when we begin to use technology, computers, to help us develop forming strategies and flare patterns considering strain. And then here at the end of our journey, using products such as COPRA FEA-RF to validate our designs. So if we look at using the COPRA tools now within our quality management, we start here where we have the geometrical design of the set of roll tools with COPRA, and we can optimize this with the COPRA deformation technology module, looking at theoretical strains, making sure we've made optimal choice there. Before we then move on to optimization with COPA FEA-RF. And then subsequent to this, we can also, as I mentioned earlier, scan our old geometry with the roll scanner to validate that geometry to make sure it 100% reflects the designed roll tools, and thus removing an additional potential problem when at the machine. So here we're looking after the design side of things, ensuring everything's good using COPA RF and FEA RF, and then the roll tools. So two of the variables now are the machine, the setup itself, and the material. So we're removing a lot of possibilities for error now. We're going to touch on this one in a little bit more detail later in the presentation. But of course, another valid reason to use CAE Technologies is the simulation of subsequent processes and testing, as you've seen here. So the next thing we're going to discuss is an example of a tube roll design with various gauges. So I have a few slides here. So if you consider making precision tubes by roll forming, it is a real challenge. There's no standard forming strategy available for tubes, and the optimum design strongly depends on the diameter of the tube itself, the wall thickness, the mill arrangement, and material properties. A roll design working well for a thick wall tube most likely will not work for a thin wall tube design. And complex, high-strength materials will probably make good and substantial know-how for a specific range of tube diameters obsolete. So in our example, we have a tube with a final diameter of 10 millimeters. We're welding at 10.4 millimeters and a wall thickness variation between 0.35 to 1.2 millimeters. And we would conduct an FEA calculation upon that. So I'm just going to give you a demonstration on this shortly, and we're going to talk about the FEA results in doing so. So here you can see how the software is dealing with the gauge variation here in the base roll set changes in the COPA RF environment. So you can see we can very quickly and easily adapt our material thickness. And here you can see the differences we can find in our FEA results between 1.2 millimeters and 0.35. You can see here the strip comparison with the actual flare pattern. We're just going to sort of have a look at the report to see what could be causing this and the differences. And of course, when we consider the gauge variation that we have here. An important thing to consider is the FEA results. In FEA results is forces when we consider deflection of our roll tools. Here you can see the forces acting upon the top axis and the bottom axis, essentially deflecting those rolls, separating those rolls, so we're not actually achieving the forming forces we would like. So I'll just give you a quick demonstration of that. I'll just prepare my screen. So here you can see a tube mill design setup configuration. So I'm not sort of going to go into the full ins and outs of how this is done within COPA, just a brief overview of the tubes module. So here in tubes, you can see first of all we have our tube mill map data. And here you can see the information upon the machine, the minimum diameters, the diameter of the bore, for example, for the top and bottom rolls, and side rolls. If we go here, you can see the types of stations we have in our machine, whether they're breakdowns, idler, fin pass, weld rolls, and so on. This is our tube mill map. Our horizontal centres, of course, and this is derived from our roll form machine. So this is the distance between the physical passes themselves. Our axes data, you can see here in the schematic what we would define. Root diameter for our profile, minimum roll widths, diameter defaults, and so on. So these are all parameters we select for our specific design. And then we define our tube mill map layout, as I said. So the type of breakdown rolls we would like to use. As I mentioned earlier, with Copa IF for tubes, everything is very automatic. Quite straightforward, not so labour intensive once this has been set up for a particular machine. To use different profiles on this machine, it's quite easy to do so. We just specify our flower, which I'm going to touch on shortly now. So once we've defined our tube mill map layout, of course derived by the machine or our rafted machine in some cases, we go on to our flower setup. So you can see here in our flower setup we've defined a 10mm diameter. We can see the contour line and the centre line for that, and we define our weld diameter. Our wall thickness here, we're having a variation, as I mentioned, in the simulation between 0.35 and 1.2 millimeters. We have a list of additions here for our fin passes, our weld addition, sizing additions, and so on. Multiple opportunities here for our strip width calculation, and of course if we have a strip width we need to maintain, we can also use that one. And we look at our forming steps, you can see here we have strategies for different arcs. So if we imagine without the software we would have to construct all of this information manually, even in CAD. Our angles here for forming as well, so we can very quickly and easily define the forming angles we intend to use. Are you all able to hear me still or not? No, it's okay. Excellent. Thank you for that. So, apologies for that. So here we can see our FEA model automatically taken through into the FEA environment. And of course we can see this if we fill our roles. Now the idea would be to conduct a simulation from here, and that would take some time. For a profile as simple as this, it could be anywhere from 8 hours to 12 hours, I would imagine, 24 at the absolute most. So if we started it now, it would be ready for the morning. I'm not going to do that for the webinar, of course. What I will do now is we'll talk about the results which were generated. So I apologise that the presentation here, or the results files, is in German, but the idea is to talk through the results and what we can see. So here you can see the 0.35 millimeter thickness. So this is a simulation for the thinnest gauge. And here, if we look at this particular example, we can see now, due to the relief we have in our roll tools for this thicker material, for the thicker gauges, the thinner material doesn't actually get any deformation here at strip edge. So ultimately we are just forming in the centre part. We're not breaking down the strip as we would like. So we can imagine the effects this will cause during the thin passes with the tube. And again we see the same effect here in station 2. Station 2 is doing a lot of work of what station 1 didn't do. Here we get a good understanding of the strain at strip edge in a three-dimensional form. So there's no remaining elongation here, just during the forming area, but it goes away. And now we begin to see some subtle differences between the design cross-section and the actual cross-section. And here in this particular breakdown we begin to see some essentially flat elements here, whereby we haven't had sufficient forming force in this area to deform the strip. Again, this can be attributed to the clearance we have for the thicker gauges. So the problem we have now is overcoming this in the latter stages of the roll train, or maybe we change the top roll. This could be a good enough reason, a valid reason for us to make an additional top roll for this material variant. In other words, to help us form this shape correctly. Again, here you can see Copra cross-section in red. This is the flare pattern from Copra. And then you see in station 8 the roll plane. Again, the differences here. A lot of material movement here, which is undesired. So the last thing we want to be doing now is expecting our fin passes to do that work in one go. Furthermore, now we can look at the contacts here on the strip. We can see where the roll is actually touching the strip. And here, whereby we would imagine the top roll would be giving contact throughout in this area, we just have a small area of contacts here whereby we're doing the forming. And in tube, this is not a good example. Here we see on the outside of the strip where we have contact. Some forming forces here at this particular area. So because we didn't bend or shape, or the material didn't assume the geometry we would like, we now have to imagine that the idler rolls as well are also doing additional work to give the material its correct position, because they're now fighting against material that hasn't been bent as we would have desired. So now we're going to look at the longitudinal strain here, and this would have been taken at the strip edge, and we can see here a high peaking strain at this particular station, and then whereby this manifests itself here, and this lots of light blue lines here as noise, which are essentially is remaining elongation. That's something to look at, but it's quite a low amount. If you look here, we're at 0.162% strain. Again, some variances between the designed and the actual. A view from above, you can see here and the strain at strip edge in this area. Of course, now because of the work being done, if we look at a three-dimensional view of the strip, we kind of get an understanding of why we may be seeing some negative effects here, because the idlers are doing lots of work to give us good position of the strip itself before we enter the fin pass. And as you can imagine now, because our shape isn't quite round as it enters the fin pass, we see lots of high force now acting upon the strip edge itself, the fin, to help it try and then form the sides of the tube which are essentially flat. And in doing so, this can of course damage a strip edge. High forces at strip edge at this point in time can lead to ripple, elongation. In other words, the material's grown in length compared to that of the base. This could give us a weak weld, a rippled weld, intermittent weld. So all negative effects. Again, here we can see some remaining elongation at strip edge now, but not a great deal, no large amounts of ripple coming through station 10. See, with this material now, we can see we have good contacts throughout the outside here in the fin, and then we come into our weld pass, and the weld is looking good. Now if we consider the 0.5 material thickness, again you can see we actually have some additional contact now in this area because of the increase in material thickness compared to the previous. A cross-section comparison here in station 5. Some high forces in this area. But if we calculate this is in newtons, this is 128 kilos, so here, as I mentioned earlier, we actually are able to get inside the machine and see on a macro level the 3D forming of the strip and get a true understanding of what's happening between stations. Something with a traditional approach which isn't possible, unfortunately. Even if we try to cut the strip from the machine and remove the top rolls, we wouldn't achieve such a good understanding of what's happening between stations. And here you can see in station 8 a comparison again between the designed and the actual strip. So it's not perfect in this example. Again, offering valid reasons of why we would need additional top rolls, and then the work being done by the fin passes to solve things. And then I think now finally we look at the thicker material. This is 1.2 here. You can see the variance at strip edge, some increasing forces now. And here we see at strip edge the differences in this area with the cross section. Our contact status here, you can see we don't get contact throughout the bottom arc in forming, just in the centre piece in station 8. And you can see here how this manifests itself in station 8 with the variance between the designed and the actual profile. We have an understanding here what's happening in the fin pass, the difference at the strip edge in this area. Again, this could give us weak weld. Those are just a few examples of using FEA to look at tube roll design. So now I'll switch back to the presentation. So in addition to that, we mentioned earlier the possibility with CAE technology, so we can export our design directly into FEA for verification. Once we've completed our design, of course, we can now use the software to generate our standard roll dimensions, our assembly plans, for example. So we can very quickly and easily generate two-dimensional assembly plans. Our bill of materials, our cutting list here that we would send to our steel supplier, for example, for cutting our steel. And then you can see here we can also generate our spaces list and our NC geometry, again for CAM this time. DXF's the polyline of the roll contour itself. Just have a few more questions. I'm assuming the sound has gone again. Okay, so yes, the webinar will be available and you'll be able to download it from the Data website, but I'll come on to that shortly. So just some of the key deliverables of the software, and of course now we can export into the Inventor interface for review in SolidWorks and Inventor actually as the 3D model our complete design. And of course in doing so we can create assembly plans over there too, or individual roll drawings. This is great for helping guys or assisting with the setup of the roll tooling. So again, another valid reason to use computer-aided engineering. So now I'll just switch back. Fortunately, it appears you guys have a black screen there now. Okay, so now I'd like to talk about some subsequent processing with CAE Technologies. So, as we've all seen, laser welding, but we can also look at the thermomechanical coupled simulation of the laser welding process as we have here. High frequency welding, you can see we have an example here of 3D electromagnetic thermomechanical coupled simulation, and this was integrated into the roll forming simulation itself. In addition to that, there's also the possibility for a 2D investigation of the weld burr flow, and this is a mechanically coupled investigation. Inline sweeping, you can see here this is an example with an open profile. And tube bending with and without a core. Stretch bending, you can see in this particular example of a H shape. And here the winding of a flexible metal tube. And these flexible metal tubes can be anything from a shower hose to the size of a deep sea riser for vacuuming oil from the seabed or from oil wells in the sea. And this is also simulated both the roll forming process and the winding itself. Deformation forces, looking at the deformation forces of rolls under load, as you can see in this example here, and the displacement which may take place. Here we have a tube drawing example. You can see here the reduction in gauge and also in diameter. Tube flange and flaring. The widening and flaring of the tube end, and of course the estimation of the process forces, quite critical here, as well as the deformation to the tube. This helps us understand the quality of the tube post-operation. Hydroforming. Possibility to hydroform a tube with either pressure or volume controlled simulation. The peeled ring process, again, which is the reduction of a tube diameter. And you can see here the development of the roll die geometry itself and also the internal mandrel. Software allows us to simulate this process as well. You can see here the example of a drawing die. You can find out more information by following us on Twitter. We tweet about our webinars, new software releases, roll forming information we may have found on the internet, where we're hosting seminars, when we attend exhibitions, lots of things like that, so you can see where and what's going on in Data M. In addition, as I was asked earlier, the video from today's webinar will be available on our website, and in addition we also have a lot of recent videos can be found on our Data M YouTube channel. And the Data M company and employees, there's a lot of us are there on LinkedIn if you'd like to find out more about us and discuss things and join some of the discussion panels we're involved in there. So all I can say to everyone is thank you for your attention. I hope you found this session informative and useful. I wish you the very best and I hope you have a good day. Thank you. Goodbye.